Well, this time we'll do just review problems. These are all problems off the review for the test. I've written them up. I'll just go through them very quickly, much faster than I would in class. Just rewind if you have any questions. Skip through the ones you don't want to see. I hope that'll make it real easy, much faster than watching a lecture. All right. I thought I'd do problem 1b. Find the point on the line, 4x plus 6y equals 52, that's closest to the origin. I give you a hint of the problem to use Lagrange multipliers. So you couch this as a Lagrange multiplier problem. Minimize the function f of xy equals square root x squared plus y squared, subject to the constraint that you lie on the line, 4x plus 6y minus 52 equals 0, if I put it all on one side of 0. The reason I do this is now it's a minimization subject to a constraint Lagrange multiplier problem. However, it's pretty tough, right? This, when I go to calculate the gradient of this, it's a little messy. I'm going to rework the problem and say, well, the square root of x squared plus y squared will be minimized when the argument of the square root is x squared plus y squared, right? Square root is an increasing function, so it's minimized when its argument is minimized. So instead of minimizing this complicated function, I'll minimize this simple one, x squared plus y squared, subject to the same constraint. With all this stuff on the left side, it's g of x, y equals 0. Now it's a Lagrange multiplier problem. Minimize this function of x and y, subject to this constraint, g of x, y equals 0. So the Lagrange multiplier theorem says you set the gradient of f equal lambda times the gradient of g, where lambda is the Lagrange multiplier, some number you don't know. And let's see, the gradient of f is partial with respect to x is 2x, partial with respect to y is 2y. Has to be equal to lambda times partial with respect to x of this is 4, partial with respect to y is 6. So I have this vector equation by the Lagrange multiplier theorem. Well, two vectors are equal if and only if their components are equal, so I need 2x equal 4 lambda and 2y equals 6 lambda, right? Now that's two equations and three unknowns. In general, that's not going to narrow me down enough. I have to also bring down the constraint. 4x plus 6y equals 52. Three equations and three unknowns usually do it. So here I divide by 2 and have x equal 2 lambda. Divide by 2, I have y equals 3 lambda. And I can substitute them into the constraint. 4 times x, which is 2 lambda, plus 6 times y, which is 3 lambda, equals 52. And now let's see, that gives me on the left side 26 lambda equals on the right side 52, and then evidently lambda equals 2. Let's move this down a bit to finish the problem. Now I can just plug that into the previous equations I had. Right, x was equal to 2 lambda, is 2 times 2 is 4, y was 3 lambda, must be 6. There's only one candidate point for the minimum, the point 46. Every minimum or maximum of this function subject to this constraint must occur at this point. How can we get a minimum and maximum both there? We can't, right? Unless it's a constant function. What's happened is there is no maximum, right? You can go arbitrarily far away and get bigger and bigger numbers, but there is definitely a minimum, right? There's a point on this plane that is closest to the origin. And this plane, yeah. And so we infer that must be the point 46, since the minimum has to be at one of these Lagrange multiplier points subject to the constraint, and there is a minimum. All right, so then the distance from the origin, you just plug this in, square root 4 squared plus 6 squared, says it's 4 square root 13 units from the origin. Close as you get. Well, let's try a different problem. Let's try 2C. Suppose I'm given this problem here, this double integral, and I want to write the iterated integral in the reverse order, dy on the inside, dx on the outside, right? So the way to do this is to first sketch the region. Since dx is on the inside, this is a horizontally simple region, right? It goes from x equals square root y on the left to x equals 3 on the right. Here's the curve x equals square root y. Here's x equals 3. And then with y going from a minimum of 4 to a maximum of 9, so you've got a horizontal line here and a horizontal line here. Evidently we have this little, almost a triangle, it's got a curve on the side that bounds the region. Well, this curve, to rewrite this in the reverse order, we now need to write y as a function of x. So x equals square root y, we square it, we get y equals x squared. Now we can say we can go from a bottom function, y equals 4, to a top function, y equals x squared. X going from a minimum of 2 to a maximum of 3, dy on the inside, dx on the outside. Well, let's try a little harder one. Some of these are sort of hard. This is a very hard one, I think. 2e. Let's change the polar coordinates and integrate to evaluate this function, which is evidently nasty, right? Integral of x squared plus y squared from 0 to a square root 9 minus x squared. When I put that in here for the antiderivative I get, this is going to be a mess to integrate on the outside integral. So what can I do instead? I notice x squared plus y squared looks like r squared. That's easier in polar coordinates. And it's over this region that has an arc of a circle out here, because if you say this is from the bottom curve to the top curve, this is a vertically simple region. The top curve is y equals square root 9 minus x squared. Square both sides to see that y squared equals 9 minus x squared, or x squared plus 9 squared equals 9. It's a circle of radius 3. That's this top curve. And then the bottom one is y equals 0. And then it goes from a minimum of minus 3 halves to a maximum of 3. So this is kind of hard to sketch. This line on the left, this line on the right, evidently is below the arc of the circle, over the x-axis, and between this horizontal line, minus 3 halves, and this point 3. So how do we integrate over that? I'm going to have to split this up into two regions. I'll say there's this triangle here, and then there's this sector here, right inside of a circle subtended by a central angle. So how do I integrate? I'll break it up into two pieces. Integral over r1 of x squared plus y squared plus integral over r2 of x squared plus y squared will give me the integral over r of x squared plus y squared. Well, let's see. X squared plus y squared is r squared. dA becomes r dr d theta in polar coordinates. I have to go from an inside curve, r equals 0, we'll say, to an outside curve, r equals 3. Oops, not so on this one. On this one, it's 0 to x equals minus 3 halves. Well, x equals minus 3 halves rewrites as r cosine theta equals minus 3 halves. Divide by cosine theta, it's r equals minus 3 halves secant theta. So the outside curve is minus 3 halves secant theta. That's this one in polar coordinates. R equals 0 on the inside. And then theta goes from this angle to this angle. This is a pi over 3 angle here. How do I figure that? It's 3 radius minus 3 halves here. This side is half as long as this side. This is a 30, 60, 90 triangle. It doesn't quite look like it. I should have drawn it a little more like that. But this is 1/2 of this side, and this is square root 3 over 2 times this side. A 30, 60, 90 triangle. So this angle is pi over 3 right here. That means I go from 2 pi over 3, this angle, to pi. There it is. Integrating the integrand r squared dA r dr d theta. Told you it was hard. Now, this part is a little easier though. R goes from the inside radius 0 to the outside radius of 3, a constant, and theta goes from 0 to 2 pi over 3. This integral is pretty easy to evaluate. It's just integral r cubed is r to the 4th over 4. Evaluated at 3 and 0 gives you 3 to the 4th over 4. Then you have to integrate d theta with respect to theta, 0 to 2 pi over 3. This one a little tougher. When you integrate r cubed, you get r to the 4th over 4. You get minus 3 halves secant to the 4th over 4 minus 0 from the bottom endpoint. And I have to integrate that with respect to theta. That's kind of a hard integral. If you pull the minus 3 halves to the 4th over 4 out, it becomes 81/4. And you have to integrate secant to the 4th. How do you do that? Remember that old trick? If you have tangent to a power times secant to a power, and secant is even, you can substitute u equals tangent. so that's what I do here. I'll substitute u equals tangent theta. Then du is secant squared theta d theta. Well, I'll break that out here. This is secant squared times secant squared. I can replace the secant squared theta d theta with du. What do I do about secant squared? Well, by the Pythagorean identity, I'll put it somewhere here. This is bad when I can't find my own stuff, huh? Yeah, secant squared is also tangent squared plus 1 by the Pythagorean identity, which is u squared plus 1. So I'll replace the secant squared with u squared plus 1, the secant squared d theta with the du, and then when theta equals 2 pi over 3, u is tangent of 2 pi over 3 must be square root 3. You can figure that out from the 3016, or from the unit circle again. And then when theta equals pi, u is tangent pi is 0, right? You can figure that out in the unit circle too. So I'll now go from square root 3 to 0, integrating 1 plus u squared is secant squared, du is secant squared theta d theta, and then this one, this integral, you're just integrating a constant, so you get 2 pi over 3 times 3 to the 4th over 4 gives 27 pi over 2. Alright, so this isn't so bad to do. I'll just finish it here just to finish it, but you can complete that yourselves pretty easily, I'm sure. Integral 1 plus u squared is u plus u cubed over 3. Plug in 0 and get nothing. Plug in square root 3 to get minus square root 3 plus square root 3 cubed over 3. This gives minus 2 square root 3. All times 8164 is added to 27 pi over 2, leaves you with this result. 27 pi over 2 minus 81 square root 3 over 32. How about that? Well, that was 2e. How about 2f? Let's see. I want to find the mass and the center of mass of a triangle, it turns out. If the density over this triangle is x, the further you go this way, the heavier it gets. Bounded by the x-axis and the y-axis and this line to make the triangle. Well, I say the mass is the integral of the density function x dA. I just integrate density to get mass over the plane region. I can cover the plane region by letting x go from the min of 0 to max of 2, and y go from the bottom curve y equals 0 to the top curve y equals 2 minus x, which I get by saying the y-intercept is 2, its slope is negative 1, so it's mx plus b minus 1x plus 2. Gives me that integration. Well, integrate x from, you get xy, evaluated at 2 minus x and 0 gives you x and 2 minus x. This is a simple integral that comes out to be 4/3. Now, to find that's the mass. To find the center of mass, I need to find my, which is the integral of x times the density function. Now I need to integrate x squared, and the good thing is you just write the same integration endpoints in dy dx. You just change the integrand and multiply it by x. Now it's x squared instead of x in here. Well, you can get x cubed over 3, put in 2 minus x and 0, and get 2 minus x cubed over 3. Integrate this one, you get 4/3. Mx is the integral of y times the density function. Well, you can pull the x out in the double integral because the inside integral is a partial integral with respect to y. I get integral from 0 to 2 of x. But again, it's this one, just y times what you had in here before. And so I integrate y from 0 to 2 minus x with respect to y, and I get y squared over 2 evaluated at 2 minus x. All times x, this integral comes out to be 2/3. Now the center of mass is x bar, x bar is my over m, y bar is mx over m, gives 4/3 over 4/3, and 2/3 over 4/3 gives the point 1 1/2. If that was too fast, you get to rewind. Here's the next one. Kind of a tricky picture on this one. Suppose I want to find the mass of a solid in 3 dimensions. Alright? Not a mass of a plane region this time, mass of a solid. I'm going to require a triple integral. I'm going to integrate the density, x again, I'll choose for the density function. but this time a triple integral since it's over a solid. How do I integrate over this solid? I sketch it. That's a big part of this, right? You just figure x plus y plus z equals 1 is ax plus by plus cz equals d is a plane. This also is a plane by the same reason. So I sketch the two planes, and it says in the first octant. So I find their intercepts on the x, y, and z axes to sketch them, right? On this one, if I put in y and z equals 0 to get an intercept, I get x equals 1, right? If I put in x and z equals 0, it tells me y equals 1, right? And similarly, I can get 0, 0, 1. These are the 3 points for this plane. It's a big triangle like that, actually an equilateral triangle, right? Now the other one, x plus y plus 2z equals 1, I do the same thing, and I get 0, 0, 1 half, and 1, 0, 0, and 0, 1, 0. So it's this triangle on the bottom, this triangle on the top. Now you can see it, what's going on. These things project down into this triangle in the xy plane, which has the line y equals 1 minus x, if you follow, so here it is. X goes from 0 to 1, y goes from 0 to 1, so this line here is y equals 1 minus x. So you integrate on the inside from the bottom curve y equals 0 to the top curve y equals 1 minus x. On the outside, the min x and the max x is 0 to 1. This covers the region of projection below the solid. And then on the inside, you integrate from the bottom surface to the top surface that you can find by solving these equations, right? Solve this for z, and you get z equals 1 minus x minus y, that's the top. Solve this one for z, you get z equals a half minus a half x minus a half y, you get this bottom curve. So I have to do this triple integral. Fortunately, it's a pretty easy one. The x can come out of here, and you just get z evaluated at this and evaluate this, take the difference. Then this simplifies a little, and you can integrate with respect to y. And then with respect to x, I'll put the rest of the problem in here. Here's the rest of the problem. This gets so complicated and tedious in here. You can see why I tore the paper in half. I made a mistake too. Anyway, you have this to integrate. What a mess. This might be nice in your calculator, actually, in this one. You can do these polynomials. So it comes out just when you multiply it out to be this polynomial, integrates to give you 1/48. There's the rest of the problem if you need it written out. Finally, let's see. Here is problem, I guess not quite finally. 3e. On this one, we want to use spherical coordinates to evaluate this triple integral of the square root of x squared plus y squared plus z squared. If w, the region over which we're integrating, is x squared plus y squared plus z squared less than or equal to 2z. What's that? That equation doesn't look familiar. There's a trick, right? We go back to the section on spheres and say if we subtract 2z from each side, it becomes x squared plus y squared plus z squared minus 2z less than or equal to 0. Actually, since it's less than or equal to it, it's significant here too. Now I can complete the square in z. I add 1 to make a perfect square, right? 1/2 of this number squared I add here to make a perfect square. Then I have to add 1 to the other side to balance the equation, get the same solution set. And now this becomes x squared plus y squared plus z minus 1 squared less than or equal to 1. It's a unit sphere, right? A sphere of radius 1 at 0, 0, 1. We just translate it by replacing z by z minus 1 in the standard equation for a sphere at the origin. So it's a sphere, and actually, since it says less than or equal to, it's the interior together with the sphere. It's the ball, the closed ball, sitting on the origin with center 1 unit above. And now we just have to integrate over that. Easy enough? Maybe not. A spherical coordinates makes it a little easier than rectangular. But here's what we can do. We look at our equation, x squared plus y squared plus z squared minus 2z less than or equal to 0. Rewrite this as rho squared, right? 2z is 2 rho cosine phi. And this is our equation, or inequality. And now you can factor this. Rho times rho minus 2 cosine phi less than or equal to 0. How can I make that less than 0? Less than or equal to 0 if and only if one of these is non-negative, I wrote positive, and one of them is non-positive, I wrote negative. That means that one of these factors should be positive and one of them negative, or at least one of them zero. So rho can be bigger than or equal to zero, that makes this factor zero, and less than or equal to this one, that makes this one zero. Then this one will be positive, this one will be negative, or zero. And those are the endpoints of rho. Phi, evidently, goes from 0 down to pi over 2, sweeping out. So this is the inside surface, the point here. This is the outside sphere. And phi goes from 0 down to the plane, pi over 2. And theta goes all the way around from 0 to 2 pi to sweep out this whole ball. So now I know how to write the integration limits. I'm going to integrate 0 to 2 pi, 0 to pi over 2, and 0 to 2 cosine phi. The integrand was rho, the square root of x squared plus y squared plus z squared, and then dv becomes rho squared sine phi. Remember that? Rho d phi d theta. So this one nicely splits into two pieces. The d theta pulls through, but significantly the d phi can't pull through, even though the sine phi can pull out because it's held constant in this partial integration. This endpoint has a phi in it, you can't pull the d phi out because you're taking this 2 cosine phi out of the integral. So we'll have to leave this as a double integral. This one is 2 pi. This one over here, what you do is you integrate rho cubed and you get rho to the 4th over 4. Plug in this endpoint and you get 2 cosine phi to the 4th over 4. Plug in 0, you get nothing. So this is the integral I have to do with respect to phi. It's an integral cosine to the 4th times sine phi d phi. We can solve this one. Remember, if you have cosine to a power times sine to a power, if one of the powers is odd, you can let u be the other one. So let u equal cosine phi, then du is minus sine phi d phi, and this integral collapses to something nice. Integral u to the 4th minus du. And the new endpoints have to change, right? When phi is 0, then cosine phi is 1, and phi is pi over 2, cosine is 0, so it goes from 1 to 0. And finish that integral easily. You get 8 pi times u to the 5th over 5 evaluated 0 and 1 over 8 pi over 5 for that nasty one. Well, let's finish up with something a little easier, huh? But maybe conceptual a little harder, even if the integration is easier. Sometimes you get an ugly region to integrate over, and you have to change coordinates into the general coordinate transformation, not something nice you already know like polar coordinates or spherical or cylindrical. Here's a plane region, rectangular coordinates. This looks like a nasty integral x plus y dA. If I tried to integrate this, I'd have to take an integral from here to here with this to top and this to bottom, an integral from here to here with this to top and this to bottom. It might be kind of a nasty integration. I can switch variables. Suppose I make a transformation, a change of variables. This is a linear transformation. G of u v equals 5u minus 5v. Au plus bv makes it linear. Au plus bv here, 10v, makes it linear. When I say this is the change of coordinates, I mean this is x and this is y written as a function of two parameters. We call them u and v. Now the Jacobian J or dxy duv, or the book calls it JAC, I think that's uncommon though, is dx du, dx dv, dy du, dy dv, and we put in the partial derivatives where this is x and this is y, and we get 5 minus 5, 0, 10. That determinant is this times this minus this times this is 50. So I have to integrate now. I have to integrate, changing the integrand in terms of u and v. I replace x with 5u minus 5v. Replace y with 10v from up here, and the Jacobian dA, this essentially, there's a little tidbit left out. This is dA in xy, this is dA in uv coordinates. So it's actually not quite the same dA. People don't like to write that down there. The book does sometimes nicely to make it clear, but to get the dA in terms of u and v, du, we have to put this Jacobian magnification factor in here. And so we get, this comes out to be 5u plus 5v, the Jacobian was 50. We have to integrate over what region? Well, the region is the difficult part. Then it comes out nicely. I took a great great change of variables for you here. Since y is equal to 10v, that tells me that v is 1/10 y. Since x is 5u minus 5v and v is 1/10 y, I can substitute in and solve for x in terms of u in terms of x and y. U is 1/5 x plus 1/10 y. So you just take the two equations and reverse them, solve for u and v in terms of x and y, by hook or by crook. And that tells you g inverse of xy gives you for u 1/5 x plus 1/10 y, for v 1/10 y. There's the inverse transformation. I can put in the four corners of that parallelogram you saw above. That's our region we want to integrate over an xy space. The origin always goes to the origin under linear transformation. I get 0, 0 back. If I put in 5 and 0 for x and y, I get 1 plus 0 is 1. 1/10 of 0 is 0. And I put in 0, 10 into this thing and I get 1, 1. I put in minus 5 for x and 10 for y, I get 0, 1. So the four corners on the new region are these four corners here. How do I know it's actually a square? Remember, linear transformation takes line segments to line segments. So if these were the corners before, if these are the corners, then I just draw line segments between them. That takes parallelograms to parallelograms, we said. A square is a special case of a parallelogram. Alright, so what we get now is 5 times 50 is 250. Integral u plus v, dv du, I should have taken it from up here. The 50 here times 5u plus 5v from 0 to 1 and 0 to 1 is the integral we get by making this change of variables. And now 5 times 50 is 250, and I integrate u plus v over the unit square. Well, that's easy enough. You come out with, well, you know what's even easier than doing what I did? Well, integrate it, let's say, and you come out with 1 for the integral, and this whole double integral just comes out to be 250 times 1, or 250. I hope that helps a lot getting ready for the test. I won't probably give you things any harder than this. Some of those integrals are a little harder than I'll probably give, but I want you to be able to do all these concepts well. So try these and send me emails as you have questions.